So the plan for today is to, use all the things we did to attack some more advanced group theoretical problems. Okay. So first of all, let's discuss a little bit how to deal with group homomorphisms. So, well, one thing you can do, for example, is to construct group homomorphisms. This is the function, or one of the functions you can use for doing this. And the idea is that, well, what you're going to do is you need to somehow know a set of generators of your group, and then with these functions you are going to assign an element of the codomain to each of the generators. Okay, GAP will check if this is indeed a group homomorphism or not. Okay, then once you have the group homomorphism, which is an object in GAP, well, you have several functions that you can use to study your group homomorphism. For example, you have image. You can test whether the morphism is injective, subjective, bijective. You can compute kernel, pre-images, and everything you want. Okay. Let's do a concrete example. So we know that there is a homomorphism from the symmetric group S4 into the symmetric group S3 that maps each transposition, which of course transpositions generate the symmetric group, that maps each transposition into, say, this one. And this is a group homomorphism, okay? So, well, you know that this is not injective and not surjective. And this is what we are going to do, okay? So, we first define S3 and S4. Then we let F to be the group homomorphism given by the following. So I'm choosing here this generating set for S4, and every element of this generating set is mapped into this transposition. Okay? Then, well, I'm doing this double semicolon because the output is somehow very long and I don't have enough space. But, well, if you just remove one of the semicolons, you will see somehow some description of the group homomorphism.
There is no sound.
Okay, and well, I have homomorphism, and then I check, for example, how big is the kernel. I check that the morphism F is not injective. I check the size of the image, and I also check, well, for example, that the group homomorphism is not just surjective, because, for example, this element, which is an element in the symmetric group S3, does not belong to the image. Okay. Of course, I can just use the is surjective, right? Yes.
Up there, if you define something that is not a homomorphism, it would complain.
Yeah, exactly. It will complain says this is not a group homomorphism or something. So you will get an error message that you can catch. Okay. So this is a very easy example, but well, now you know that you can also work with group homomorphisms. Okay, this will be useful. What's wrong here? Okay. Oh, I don't know. I'm having problems with my presentation. I cannot switch pages. Why?
Oh, sorry, I just moved it.
Did it change something?
I changed it back.
Okay. No?
Oh,
sorry, I just... We're having a small problem with it. Okay, now I think it is good.
To use the mouse because with the
very good. So, now, you have some very natural group homomorphisms, right? In particular, well, you know that you can compute quotients, right? And, well, you have this canonical surjective map into a quotient of a group. So how can we deal with this map? Well, the function is this very, very long function, natural homomorphism by normal sample. So if you use this, then you can construct a canonical map into a quotient. Okay? Here you have a very, very easy example. So what I'm going to do is, first of all, define the cyclic group of size 12. Remember that typically all my groups will be written in multiplicative notation. I'm going to represent this as a group of permutations. Then I'm going to compute this subgroup and the quotient. Okay, and I want to see, well, some properties of this canonical map. Okay, canonical surjective map. So now I'm defining the group in a different way, but of course it's the same as using the functional cyclic group, right? So I define this permutation of length 12, and then I define the group, which is the group generated by this. I think that a square bracket is missing here. We should check this, but maybe a square bracket is missing. Not sure if this is going to work. I think it won't. Okay. Then I define K as the subgroup of C12 generated by this power of G. And then I define M as the natural homomorphism by normal subgroup, well, given by these two. Okay. G and K. And what you get is this homomorphism. So the generator is mapped to this, well, crazy element that I don't understand. Okay, because for this I have a presentation which is somehow difficult to understand, but it doesn't matter, right? It has, well, generators, and this G is mapped into the first generator. Okay, and then I can test something. For example, that G6 should be inside the kernel, which is clear, right? And well, it is, right? Good. So this is an exercise for you. It's not a hard exercise, but it is nice to play a little bit with this. So what you have to do is to verify the corresponding theorem between, say, G and a quotient. So you can let G be the cyclic group that we used in the previous slide, and this particular quotient, and then you need to test that all subgroups of G containing K are in bijective correspondence with subgroups of the quotient. But you can see this, concretely by hand. Very good. So, what else? Well, of course, you can compute automorphism groups with GAP, right? With this, you can compute the automorphism group of a finite group, say, and some infinite groups also are possible to put there. But okay, let's see. If G is a group, the automorphisms of G of this particular form, given by a conjugation of a fixed element, are known as inner automorphisms. Okay. Well, if you want to check whether an automorphism is an inner automorphism, of course you have this function. Okay. So let's play a little bit with this. Easy example. So we are going to compute the automorphism group of the symmetric group in 3 letters, which you maybe remember that this is indeed S3, right? It's isomorphic to S3. So we define here the symmetric group, and then we compute the automorphism group. This will be saved here without this variable, and then I check, for example, that this group is not abelian. Since it has size 6, then it is enough to this information is enough to know that this group is isomorphic to S3, right? But you can do some more complicated stuff. For example, it is well known that each automorphism of the symmetric group in n letters, if n goes from 2 to 5, is inner, right? And well, here you have a proof with GAP. So we run over all n's from 2 to 5, we define the symmetric group as n, and then we check whether all automorphism is inner or not. And it is, right? The nice thing is what happens with x6, right? Let's do this. So, you see that step by step we are just doing more complicated things, right? So you know that in X6 there are non-inner automorphisms. Let's check this with the computer. So first of all, we define a group, and then we count how many automorphisms are not inner. And this is precisely the number. Okay? We are using all the things we know, right? Like number and all the functions we know. Well, if you want, for example, to see how one of these group homomorphisms look like, you just need to do something like this, right? Here we are doing the same as we did here, but instead of counting how many of them we have, what we are doing is just, well, take the first one, right? And if we do this, well, you get this homomorphism. So what what this means is that, well, your group S6 is generated by this transposition, and this 6 cycle. And then one of the inner automorphisms maps this guy to this permutation and this transposition to this involution. Okay?
Yeah, that's not actually what you wrote on the slide, but that first 1, 2 should be 162, 3, 5, right?
Sorry?
Oh, so Gap gave the right.
Oh, yeah. This is I think, yeah, this is wrong, right? It should be this one.
Right.
Yeah, thank you. Yeah, it's a typo. Yeah. So if you try to do this yourself, you might not get the same result, right? Because typically Gap uses some random algorithms or uses some random elements for doing something, and maybe the first one you get is different from that one. What is clear is that this is one of the group homomorphisms, right? But maybe you will get, if you use this function first, you will get a different one. Maybe not, who knows? Okay? And okay, so if you want to, now you know that you have a lot of group homomorphisms which are not inner. We have one, which is F. Let's try to see something about F. You can, of course, compute the image of this morphism, right? Like the graph. But well, I need a lot of space for doing this, so it's better just to tell you how to compute 1 or 2 values, right? So if you want to know how the value of the transposition 1, 2 under F, well, this is what you have to do. Remember that Gap acts on the right, so this is like the notation. And here you have another value, okay, which can also be computed in this way. Right? But remember that you are acting always on the right. This looks like you're acting on the left, but good. So you can also compute homomorphisms in general, right? So this function, for example, all homomorphism will return the set of group homomorphism between 2 given groups. This is a very useful function, but not very efficient. Okay. But well, and you have some variants like, for example, all endomorphisms or okay. So just as an easy example, there are 10 endomorphisms of the symmetric group S3. This is just what I'm doing. Okay. Okay, so here is another example. So what I'm going to test, again, is an elementary property or elementary exercise in group theory. So I want to compute the center of this product, the cyclic group of size 2 times the symmetric group S3, and I will test that this group is not stable under endomorphisms of this group. Okay. So the center of this group is not invariant under endomorphism of the group. So first of all, I'm going to compute the center, and then I'm going to see that there is at least one endomorphism that permutes the non-trivial elements of the center. Another type. Sorry. So first of all, I define C2, then I define S3, then I define the direct product, and I compute the center. And you see that this is the center, precisely what I wrote here. And then I check, well, if all endomorphisms are invariant or not, and the answer is no. Okay? So this is another well-known fact, right? So if you compute the automorphism group of S6 and you divide out this by this normal subgroup, the inner group of S6, then you get a group of size 2. Okay? How can you do this? Well, you know you can define the automorphism group of a group with this function, automorphism group. And you can also compute the group of inner automorphisms with this function. Inner automorphism group. It's a long name, but well, this is what it is. So in this case, I'm computing S6 and its automorphism group, which has this size. And then I'm computing the inner automorphism group of A, which is I. I'm not printing the output because, well, I need a lot of space. This is the only reason. And then I compute the order of this quotient, which is, well, which is 2. Okay? Good. So this is the same thing as before or not? I don't know. I think it is the same example of. No, it's a different one. Okay. But okay. Maybe this is not so interesting because it's pretty much what I did at the beginning, but okay. So here what I'm doing is to define a particular group homomorphism between S4 and S3 given by, so here I'm using a different set of generators, right? So this like, I don't know, elementary transpositions or something like this, transpositions of the form I plus 1, you know that this transposition generates my group, and I'm sending, well, this 1, 2 to 1, 2 to 3 to 3, and 3, 4 to 1. And then I do some calculations in my group, okay? So like computing the kernel, and the kernel is this line of size 4, and I check, for example, that my group is injective. Sorry, but my morphism is injective, but not injective and subjective. It's really similar to what I did at the beginning. Good. So now I'm going to do something more advanced. Okay. So we are going to see what is. So what kind of information GAP has. So in particular, something really useful that GAP has is an database with all groups of, say, small order. Okay. The library is known as small groups library. So here you have a description of the library. So essentially what you have here is a huge database of groups. You have all groups of order less than 2,000 with this exception because this is a huge number and it doesn't make sense to include all this group there because the list is too big. You have the group, also you have group of cube-free order with compound, several different P groups, I don't know, groups of square free order. Oh, it is there. Sorry. Yeah. Well, something is missing here. Sorry for this stuff. But you have several different families of groups, right? Groups of order, for example, q to the n times p, where q to the n divides one of these, and p is different from q. I mean, it's a huge library with several things. We are going to use this to prove theorems. Okay, so let's see how it works. So say that you want to know something about groups of a particular order, say order 12. You know that there are 5 of these groups, right? And you can describe these groups using semi-direct products. This is a classical exercise in group theory, but well, if you want to know what GAP knows about those groups, this is the function you need to use. If you use this function, and then you will see somehow a list with the information GAP contains about those groups. Okay. For example, let's see how this works. So this is a very easy exercise in group theory, right? We are going to prove that there exist non-abelian groups of odd order that are the and that the smallest of this group has order 21. Okay. Right. Well, you can do this. So you run over all small groups of size from 1 to, so odd order, I'm using this range, odd order up to size 21, and checking or keeping only those that are not abelian. And I do this and I get one, okay? So I'm returning the first one in this list, and I'm just checking the size, which is 21, okay? Is it clear what I did? So I'm running over the list of all groups up to size 21. Of course, you can put something bigger here or something smaller, but I mean, I can put 100, but then I will stop at 21 because the smallest example is 21, right? So, well, I run over all of these, avoiding to check, for example, groups of even order because I'm not interested in those groups, and then, well, I find something to prove this. Okay, let's go a little bit further. So another exercise. You have no simple groups of order 84. Typical exercise in group theory. So we're going to do the same as before, but with a different thing, right? So we are going to run over all groups of size 84 and keeping only those that are simple. Right? Using this filter is simple. And the answer is nothing, because all of them have normal, non-trivial normal subgroups. Okay. Well, let's say that now I know that I have a list, for example, of all groups of order 12. Right? What can I say about these groups? Well, GAP has a function which is useful. The name is structure description, and with this you can have some idea about the structure of your group. Okay, but this is tricky, right? So if you, what I'm doing here is producing a list of all the structure, all possible structure descriptions of group of order 12. I have 5 groups. This is one of the groups. Okay, dihedral group, alternating group. Then I have a cyclic group, and then I have this semidirect group. This is the notation for semidirect group. But you have to be very, very careful with this, because first of all, this is a semidirect product, so it's not clear how is the action of this into this. In this case, of course, it is because you have only one. But I mean, in general, you can have the same, for example, the same string, and for 2 different groups, right?
And would it only give us one string in that case? And
Sorry?
would it, if there was more than one semidirect product, would it give it twice the same description, or would it only?
Maybe yes. Maybe yes. Yes. So the importance, I mean, this is very, very useful, but it's not an invariant. Okay? This string is not an invariant. So it's not an invariant. So you can have, for example, non-isomorphic groups with the same string, and you can have 2 isomorphic groups with different strings, right? This is clear, right? Because, for example, you can have dihedral group, right? You know that you can describe the dihedral group as a dihedral group or as a semidirect product with the cyclic group of size 2, right? So maybe you have 2 crazy presentations of your group. And well, if you apply the function structure description to one of these things, you find that this is a dihedral group, and maybe if you apply to the other presentation, what you get is a semidirect product, right? This can happen. So it is not an invariant. But I mean, that's okay. Yes, this is not bad. It's just something that can give you somehow a hint of about the group, right? So let's see a concrete example. So there are 2 groups of order 20 that can be written as a semidirect product like this, because you have 2 actions, right? 2 very, very different actions. So, but structure and description will not distinguish these 2 groups. You see, I'm doing the same as before, but with groups of size 20. So I'm running over all groups of size 20 and computing this structure description. And this is what I get, right? I get these 2 things which are completely non-isomorphic, and then other groups.
This is warning that there's more than one.
Yeah, but I mean, it is interesting, because now you do this and this, and you say, okay, there is an action doing something, there is another different action doing something. Okay. You need to work a little bit if you want to know more about the action or whatever, but there is some information, right? And I mean, since you have a library with a lot of groups, then you have a way of identifying your group with groups in the library. And this is an invariant. The function is id group. If you apply id group to some group, then what is what you get? For example, if you apply id group to the symmetric group, this is what you get, 6, 1, which means that your group is the first group of the groups of size, the first group appearing in the list containing groups of order 6. Right? Let's apply this to symmetric group 4. This is what you get. So it means that in the list of groups of size 24, your group appears at place 12. Okay? And well, here you have other examples. And this is an invariant. Okay? If you apply this, for example, If you apply ID group to this one, you will get, I don't know, number 1, say, and to this one, you will get number 3. Right? Very good. Is it clear? So now, real mathematics. Okay? So, Lam and Dyck proved a theorem stating that each index 2 subgroup of this automorphism group is isomorphic either to this symmetric group, to this PGL group, or to the Mathieu group M10, which is not simple. Okay? So what I'm going to do is to check, to prove this with Gabi. Okay? Here you have the reference for the paper, and I'm going to prove this theorem with Gabi in a very easy way. So, first of all, I compute the automorphism group of S6. We know how to do this. Okay, I did this. Then, MST is a list. The list of all subgroups of index 2 of the automorphism group. We know how to do this. Okay. Then I produce a list with the ID group of all the groups appearing in my list. Right? So this is what I get. So all groups has the same size, 720, and these are the numbers, the positions, right, in this list. Okay, so it means that I have 3 subgroups of index 2 here, which are these groups. Okay, can I understand the structure? Well, you can try to, yes.
The list is 720, and the position is 760.
Sorry, this is the size and this is the position.
Oh, this is the size.
Yeah, the first one is the size. So, okay, 3 groups of this size, and these are the positions. And okay, so you can try, for example, to apply structure description to all these 3 groups, but this is maybe not a good idea because you know this is not an invariant, right? Maybe you get some nice results, maybe not. It is better to compare these groups with the groups you are expecting, right? So you see, the ID group of this guy is this. So the first one is PGL29, that one. The second one is this, right? 763, which is the symmetric group S6. And finally, this Mathieu group is this one. So the theorem is proved, okay? In I don't know, 5 seconds.
You could also ask, is isomorphic instead?
Of course you can do that. Yes, sure. Yeah. But yes. You can do this. But here what I'm trying to explain is, well, this particular library and how to use this library, right? Yes.
I'm surprised that the function subgroups of index 2 only returns 3 subgroups, where there must be many more, right? I mean, it's returning the isomorphism classes or the actual subgroups?
I think subgroups, right? Because they are normal, so I mean, they are normal, so up to conjugation, they are normal. So you don't have different conjugacy classes, right? Mm-hmm. So yeah.
But you could still have, for example, 10 subgroups, but they're all isomorphic to these 3, right? I'm surprised. Is it true that there are literally only 3
okay.
subgroups?
If you don't have copies of this, I think it's the full list, but yeah.
Yeah, because they are characteristics.
Yeah, they are characteristics. So yeah, they should be the full list.
Interesting.
Yeah. Okay. Yes.
Just to make sure that the ID group would return size and the position in the list, not the length of the list.
No. The size. This is the size of the group, and this is the position.
Because I you mentioned in the slide before that this is how much we have, and this is the position of the list. Or is it just a different?
Don't know.
So,
maybe I made a mistake, but no.
No. Okay. The list is this list of all simple groups up to size 20,000 with some restrictions, and this is position in that.
According to the size, right? Good. So another result. So typical thing that you do in a group theory course, commutators of groups. So some group is different from the set of commutators, right? And it is not very easy to find an example. The smallest example has order 96. This was proved by Robert Guralnick here. I think this was his PhD thesis. Okay. So what he proved is precisely this: that the smallest group, such that this and these two things are different, has size 96. Well, it is super easy to do this with GAP, right? Because we have all the groups. So with one line, you get this. So what I'm doing? Well, I'm just running over all groups of size from 1 to 100, say, and then I'm gonna keep only the first one, where the order of the commutator subgroup is different from the order of the set of commutators. You see, this line is to compute the set of commutators, right? I mean, you need to think 2 seconds. The only thing I need to explain, I think, is just what is this? Well, this is just the expression for returning a commutator, right? But that's it. And then, well, you get order 96, right? So it means that you have an example, which is different from this example I found in the book of Carmichael, right? But, okay, what if I want to present this example?
Sorry, I forgot my group theory. So the commutator group is just generated by these commutators?
Yes, it's the group subgroup generated by all commutators.
So in this group of order 96, some product of commutators is not a commutator.
Yeah.
Right. Thank you. It's been a while.
Yeah. But okay, so you have an example, right? But say that you want to present this example in some way. Of course, you can say, okay, it's the group. You compute the ID of this group, and you say, okay, it's the group with ID 96 something. Well, you can do this, but nobody. I mean, who can understand this group? So I'm going to give you a very explicit presentation of the group, which is pretty nice. I think it is the best thing I can get, right? But I'm going to use several advanced tools for doing this. What I'm going to do is to show you that this group is isomorphic to this permutation group, generated by these two permutations inside S12. Okay, I move with 12 points. So how to check that my group G is isomorphic to this? Of course, I can use ID group applied to this and to this, which is this. Or I can use isomorphism groups, and then I check that this is okay. I'm doing this with ID group, right? Nice, I gave you a nice presentation. But where this come from? I mean, how can I get something like this? Well, I was lucky, but you can also be lucky. You just need to know what functions to use. So this is what I did, and this could be very useful. Okay, even if you are working on a concrete problem, these tricks that I'm doing here maybe are the key. The difference between being able to compute something and not being able to compute something. So we have our group, right, G. Now I'm going to transform my group into, I am going to find a permutation representation for my group. Why? Because it is better, right? Something that you see. Okay? So for this, I have this function, isomorphism per group. This function will return, if it is possible, a permutation representation of my group, or more precisely, an isomorphism between my group and a permutation group which is isomorphic to this. Okay?
This is not like the left or right regular thing.
No, it's something. I don't know which is this thing. I mean, in general, I don't know, I don't remember, but I would say this. I think it is not the regular representation, but in any case, you don't need. I mean, you need to do something to it because maybe this is too big. Maybe it is the regular representation. I don't remember. We need to check the content. But in any case, you need to do something else because you want a better representation, right? So, because you have I think you have a function for computing the regular representation. So. Then you can do something like this. You have another function which returns a smaller degree permutation representation. Be careful, I'm not claiming that this is the smallest degree representation. So you apply this, and maybe GAP finds a better representation, moving less points. Maybe not. I mean, maybe you apply this function again and it finds the representation because it is based on some random thing. So if you try to do this now, maybe it will not work, maybe it will work, maybe it will work after 5 attempts, or maybe you get something moving, I don't know, 12 points, but in a different way. I mean, maybe you will never get the same result as I found. But in any case, if you try hard, then you will get an answer, okay? So what I'm doing first is the following. I have my group. I convert my group into a permutation group. And then I use this function to try to, move less points, okay? Trying to change the symmetric group contained in my permutation into something which is smaller, okay? Okay, as I said, this degree maybe is not minimal, but well, at some moment, you convince yourself that this is the best you can get, right? And that's it. This is how I found this. And then, of course, I need to present this not by a group generated by, say, 50 permutations, but I want 2, 3, or a small number. And for that, this is what I use, small generated set. Again, this is not returning a minimal generated set, but it's returning a small generated set, which in my case was 2, which is minimal, right? Okay, because my group is not a medium. Is it clear? So you can try this, it's a nice exercise, and maybe you will get the same thing as I did, maybe not. You will get another one. I think that you cannot reduce this 12, but I'm not sure, right? But I'm pretty sure that you will not, but you can try. Is it clear? So let's try to see a different thing, a theorem of Navarro. So, okay, so I'm going to prove a theorem of Navarro. So you have a group G, and then you have this invariant, CS of G is the set of sizes of conjugacy classes of G. Okay? This is the notation for conjugacy class, and this is CS of G. For example, we know that S3 has 3 conjugacy classes, the trivial one with size 1, the class of involutions, which has size 3, and the classes of 3 cycles, which has size 2. Here, CS of my favorite group is this. Okay? Good. So I write a function to compute this CS. Right?
This is a set, not a multiset.
I'm doing this as a set. Okay? I mean, you want to study this as a set, not as a multiset. Of course, you can just replace this by the multiset, but since I want to answer a question, a particular question, a concrete question, it's about sets. Okay? So, well, this is easy. I have my group. Then I compute all conjugacy classes, and then I just make a list with the sizes of these conjugacy classes, and then I do not keep the list of the multiset, but the set. So I kill repetitions. So, and then I check these 2 things. Well, I check with my function. So everything is okay, right? Now the real stuff. So, notation, which is important. So remember that we have an IG group, right? So I have a group. If I apply an IG group, I'm gonna get something at least like this, where this is the size of my group and this is the position, right? Let's say that G and K is, well, a group isomorphic to a group with ID and K. Is it clear? So if I say let G be G and K, well, what I'm saying is that I'm taking the group of size M with that is located at position K in my list. Okay? Notation. Is it clear? Good. Now, Navarro proved 5 years ago or 6 years ago that there exist finite groups G and H such that G is solvable, H is not solvable, and CS of G and CS of H are equal. Okay? This was a question of Blau. Okay? So I don't know, maybe from the 60s or something like this, Navarro realized that, well, with computers you can do this. Okay? And here is the proof. So in this case, well, you need to be a little bit more clever. Just running over the list is not enough, right? Because the list is not big enough. But this is what Navarro did. So first of all, I define this G, this direct product, okay? Right? And then this is H, this different direct product, okay? Okay, so I don't know how Navarro found these two groups, but one thing you can do is, first of all, you check your list of small groups. If you cannot find a counterexample, and you really believe that there should be a counterexample, then the next thing you will do is to try to run over Cartesian product of the small groups, right? And this is how you find this. After maybe 1 week of calculations, I don't know, but this is how you get this. So I define U and V, L and K, which are, okay, U is this, V is this, L is this, and K is this, okay? Then I define U times V and K times L using, well, what we know, and then I check that one function is solvable and the other is not. So I'm almost there, right? I just need to check this. Okay, and now what? Well, you can just try to apply CS to these two groups. But if you try to do this, then, well, the computer will need some time. So it's better to remember that we are, you know, mathematicians, right? So in this case, it's better to use a trick to compute these conjugacy class sizes, okay? And well, what you need to use is that you know precisely how to deal with conjugacy classes of a direct product, right? So CS of U times V is just this, okay? It's this set. Then if you use this, then it is very easy to check, for example, that, well, I don't know what is this line. What is this?
Yeah, you take a conjugacy class.
Yeah, and then just the equality of these two, right? Yeah. So here, for example, for this group, it's very easy to check the size of conjugacy classes. For the other, it is not, but then I use this trick to check, and I found that these two things are the same. So I have a counterexample or an answer to this problem posed by Brown, okay, which is real mathematics. Check whether this is trivial or not. And again, God is able to recognize the trivial group despite the crazy presentation, right? In general, remember that this is a super hard problem. But well, I mean, don't be afraid. You should try, because maybe you can get an answer. So let's continue with this. Now that we are, I mean, it seems that we can do some stuff, right? So let's continue. You know this super famous open problem, right? Burnside problem. So the problem, I'm not stating the problem in full generality, but it is enough to state the problem in these terms. So you define, for each n, you define a group like this. So it's generated by A and B and an infinite set of relations. So the relations are that every word that you can make with A and B to the n will be trivial. Okay? And the question, which is a very old question stated by Burnside, more than, I don't know, 100 years ago, is if this group is finite or not. in general, the problem is almost solved, but there are some cases that are open. Okay?
But V35 is infinite or something.
Yeah, I think so, yeah. But this one, this is open. Okay? This case is still open. And I think that if you put here a 7 or an 8, it is also open. Don't remember precisely, but some cases are still open. Okay? So, let's see. So if you put a 2 here, if n is equal to 2, this is a very easy exercise, right? But if you put a 3, it's not so easy. This was proved by Burnside. So we are going to recover the result, but proving this with God. But this is funny, right? Because how can we deal with an infinite number of defining relations? We don't need to. Okay? So this is what we are going to do to prove that this group is fine. So we are going to do this. So first we define f as the free group with 2 generators. And then we are going to divide f by the normal subgroup generated by all these relations. So I randomly choose a big number of words, and then I put all these relations, right? Each of these, W1, W2, W3, are some randomly chosen words of f. Okay? And then with this, I can prove that my group is fine. I cannot compute the order with this calculation. I mean, with this, I know that my group is a quotient of this, right? But who cares? It's fine, and that's it. I define a free group, then I do this. Relations is, well, this set, right? This number should be quite big. If you try this yourself, well, I mean, maybe you don't get the answer, right? You need like try again, or maybe make this number bigger, who knows? But I was able to do this. I define this particular quotient, and then I compute the order. Oh, that's it. It is. So you don't, I mean, if this number is big enough, apparently this is enough, right? I would like to understand better what is behind this, but I don't know. I mean, but it's a nice way of proving this case, right?
I mean,
Which is, the original proof is a collection of smart tricks using commutators. Yes?
is this actually equal to the group?
Yeah, it is. But this, I mean, this, I'm not claiming this.
This is not proving this.
Yeah. My calculation is not proving this. You need to you need to go one more step further back. Similar thing. This was a theorem of I think Sanov. This one is also finite. And what we are doing here is to prove that this is a finite group of order at most x. Same trick. I created this randomly chosen set of words, and then I divide my free group by this set of relations, and that's it. Amazing, right? Because this is really, I mean, and this is really hard to do. This is not easy. I think that, I don't know, maybe in this book of Hall, Proof Theory of Hall, you find this proof, but it's not easy. A different thing, a problem of Djokovic. So I was reading this journal, and I found this problem. So you have to prove that the alternating groups an for n bigger or equal than 5 and different from 8 can be generated by 3 conjugate involutions. Right? 2 years later, this guy published a solution, but he was not able to know or to say what happens in this case. He wrote in this solution that I don't know what happens here. Well, let's solve this. Okay. So, what we have to do? Well, we will write a function that finds all possible conjugate involutions that generate the whole group. Okay? I'm not claiming that my function will be clever. It's just a naive approach. And then, well, we check what happens. This is the function, okay? So I have the alternating group, I compute all conjugacy classes, and then I run over conjugacy classes. I take the order of if the order of the representative of the conjugacy class is 2, then well I create a subset with 3 elements. You see here I'm using something different. I'm not creating the full list of all possible subsets, but I'm creating this step by step. Right? I need to use this iterator because otherwise I won't be able to compute the full thing, because well the amount of memory needed to do this, to put all this in one list, is too big. I think we discussed this maybe yesterday or the day before, but this is an interesting trick, right? Really neat. And then well, I check whether this set will do what I want or not. This is my function, very naive, with this only thing which is extremely important, right? And then, well, let's play a little bit with this. If I apply this to an S5, well, of course, I can see, for example, that S5 is generated by this, and this, right? So this is because, well, this is what I get. And I have 380 generating sets that fit into this problem. Okay? But if I try to do this for okay. If I try to do this for this alternating group, then this will not work. Okay? I need some minutes, but after some minutes I get no answer. So there is no solution. Okay? So this problem is solved. Good. One more. Same journal. Problem of Dixon. You know what is the commuting probability of a group? So I have a finite group. I choose randomly 2 elements, and I ask which is the probability that these 2 elements commute. Okay. So if you know this formula for counting the number of orbits that you have when you have a group acting on a set, right? This, I think it is Burnside or Frobenius, or I don't know. Burnside, yeah. So this formula, if you apply this formula to this problem, you get that this commuting probability is the same as this: k of g divided by the order of g, where k is the number of conjugacy classes of the group. Okay, should be written there, but it is not. Okay, so I'm writing this probability function here. So I compute the number of conjugacy classes of my group and divide by the order of the group. This is the commuting probability of the group. Okay? So Dixon observed that the commuting probability of a finite non-abelian simple group is always less or equal than 1/2. Okay? His proof is not very hard, but it's based on some Dyck classification theorem that you can find in this Gorenstein book. But I'm going to present a different proof using that for all simple groups, right? So first of all, well, the bound is sharp because, well, this is precisely what you get in the alternating group 5 in 5 letters. Now, so the problem or Dixon's proof appear in the Canadian Mathematical Bulletin, and here I will present another proof given by one of my students. When I was teaching group theory, and I gave them this problem, and this guy found this very smart proof. So I'm going to sketch a little bit the mathematical part. It's not hard, but just I want to use the computer. Okay. So we first assume that the commuting probability is bigger or equal than 1/12. Since G is a non-abelian simple group, the identity is the only central element. This is clear. So first, we are going to assume that there is a conjugacy class of G of size n with this n. Okay? Then, so G acts transitively on this conjugacy class, right? So it means that G is a transitive subgroup of the symmetric group. But what is a transitive group? Well, transitive group of degree n is a subgroup of the symmetric group Sn acting transitively on this. Okay? And GAP contains a database of all transitive groups. So it means that I can just try to run to search into this library for groups playing this role. Okay. So now that I understand this in these terms, the problem is not very hard, right? Because what I'm going to do is to show that there are no non-abelian simple groups acting transitively on sets of size n, where n goes from 2 to 12. And of course, with this commuting probability. Okay, that this thing that I'm waiting to find here will not appear. Okay? Let's do this. So I run over all transitive groups, moving 2, 3, 4 up to 12 points. Okay? That are simple and non-abelian. I create the list of groups. And then, well, I have a list which is L, and then I compute the commuting probability for all these groups. This is the list of commuting probabilities. And well, all these numbers are less or equal than 100. That's it. At least for this part of the this part of the problem is solved. Why? Well, because I have a list of transitive groups.
So commuting probability is already a function.
Yeah. I defined this I defined this at the beginning.
Oh, okay.
I think here, this line.
Okay.
Okay? Very good. And then for the other case, well, now I assume that all non-trivial continuous classes of G have at least 13 elements. Then I use the class equation and I get this thing, right? I play a little bit with the class equation and then, well, just, again, doing something here, I get this. So it means that I need to check all groups of size less or equal than 144. Again, I run over this library, small groups library, and well, I find that A5 is the only example which has probability 1/2, and that's it. Okay? And to finish, I give you this exercise. So transitive groups are either primitive or not. Okay? So primitive groups are transitive groups with some extra property, right? And I don't want to get into details, but it's not very hard to understand this definition. But the thing is that GAP also contains a database with all primitive groups of degree up to this number. Okay? In this nice book of Peter Cameron, Permutation Groups, you will find these two exercises. So you need to prove that there is no sharply 4 transitive group of degree 7 or 9. It doesn't matter what these things are, but you can easily prove this with GAP. And the same happens here. Primitives group of degree 8 are 2 transitive. Again, this is an exercise that you can easily solve with GAP using the library of primitive groups. And of course, well, you need to know how to test, for example, 4 transitivity or 2 transitivity, right? This is an interesting exercise from the computational point of view. Of course, from the mathematical point of view, it's more interesting to do this just by hand, right? But well, this is, that's it. Thanks.
Thank you.